This video provides a bit of an explanation for why I deviate from a standard textbook approach to thermodynamics and take a statistical point of view. The main reason is you need to learn thermodynamics, and learning requires organizing ideas and facts in a logical framework. For thermo, energy and momentum, and a statistical application of Newton's laws provides that framework. Now, why is learning it so important? Well, the short answer is that engineers, and physics majors for that matter, and chemistry majors for that matter, have to pass a thermodynamics class somewhere along the line. And those classes, like a circuits class, goes well beyond what you learn in physics. The problem appears when you need to relearn what you quickly forgot from chemistry and physics. If you have to relearn things, that will make the new material even more challenging than it should be. Now, for some reason, I think it has to do with the studio physics class at Florida State. FSU and FAMU students in mechanical engineering struggled a great deal with thermal fluids, so much so that they had to turn part of the ME Tools class into a remedial thermodynamics class. They once used only one lecture in ME Tools to review 3 weeks of basic physics on thermo before teaching the basic thermodynamics of a Stirling engine. They also were drawing and building that Stirling engine in that course. Anyway, I was told by a former student from TCC that this did not go well. No one knew what was going on, and it got even worse in thermal fluids. So why is thermodynamics such a problem? Well, I think the challenges are time. The subject always shows up at the end of the semester where it gets a short shrift. If people spend more time on mechanics like they do in the studio physics class, there won't be enough time left to do thermo. There's also a lack of logical structure in our textbooks. The approach is more like stamp collecting than science. You may not know about stamp collecting, but if you got stamps on a single topic, where do you put them? Do they go in different sections based on when or where they were produced, or their dollar value, or they go together based on their topic? Many choices can be made. You might even base your decision on whether or not they're a pretty color. Chemistry uses bits and pieces of thermodynamics here and there, and they rarely tell you that specific heat and ideal gas laws follow from Newton's laws. It's very phenomenological. Physics textbooks always include the kinetic theory that predicts these results, but sometimes scatter it into 2 or 3 different chapters, sort of as needed. And professors sometimes ignore it completely, and sometimes ignore it if they're short on time. But I think there's another reason. Statistical mechanics is modern physics because it wasn't really properly completed and certainly not confirmed until the 20th century. Many people ignored the early ideas, especially those developed in the 1800s, because there was a lack of experimental evidence that atoms were real. And I think you need to understand that atoms were not always believed to be real things. And the assumptions of statistical mechanics and the kinetic theory of gases is that matter is made up of atoms. Those atoms interact via forces, sometimes very short-range forces. And then there are collisions between those atoms, or they're particularly in a gas. Those collisions will conserve energy and momentum. Motion is fairly random and involves a very large number of atoms. So you use statistics to calculate average values. You don't solve 10 to the 23rd equations in 10 to the 23rd unknowns using Newton's laws. Instead, you average over the effects in those equations to take a statistical approach to doing mechanics. That's where it gets its name, statistical mechanics. The kinetic theory of a gas is based on the idea that atoms and molecules are really small, especially compared to the distances between them in a dilute gas. There are no long-range forces. What forces there are assumed to occur only during elastic collisions between those gas atoms or molecules. The averaging process shows up when you define gas pressure as the average force per unit area from the impulse due to collisions with a wall. And temperature is an average kinetic energy. For example, in this little picture here, on the left, we're applying heat to a container where all of the molecules are at rest. The center of mass is at rest, and the molecules are at rest. That heat adds thermal energy. That turns out to provide a random kinetic energy to the various molecules or atoms inside of that box. That random kinetic energy leaves the center of mass at rest. So the object itself is not moving. It has no kinetic energy to an outside observer, but it has internal energy that we measure with temperature. That heat that we add makes the thing hot. Use those words carefully. Heat means to add energy to a system, whereas temperature, what we also might use the word hot to describe, is describing the average kinetic energy of the molecules inside of that gas. This idea is quite old. It was proposed by Daniel Bernoulli in 1738 for Boyle's law, developed throughout the 1800s. It predicts a number of things. It predicts the ideal gas law. It also predicts the specific heat of a gas, especially a monatomic gas, but also diatomic gases like oxygen and nitrogen. It predicts, in work by Maxwell in 1873, the speed distribution of the atoms in a gas, something that is in principle observable. But the problem was atoms. Atoms were used in chemistry, but they were assumed to be a convenient hypothetical, something you use to make equations balance and figure out how to make things, but those atoms had never been observed. Physicists in particular took a very dim view of the use of atoms in chemistry. And to establish that this is modern physics, the Nobel Prize in 1926 went to Jean Perrin for showing that matter was discontinuous. He did Brownian motion experiments in 1908 that tested Einstein's 1905 predictions about Brownian motion. The Maxwell velocity distribution I just mentioned, it wasn't confirmed until 1920, where people could measure the speeds of individual atoms coming out of a container and see that the number of molecules with a particular speed varied according to the Maxwell distribution you see in this picture from our textbook. It's also easy to forget the electron was not observed until 1896. Prior to 1896, electricity was a fluid. Even as late as 1910, an atom, such as it was a droplet of positive charge with some electrons in it. That model has no explanation for why we have elements, why those elements have specific masses or a particular atomic number, or why they belong in a periodic table. There's no connection between the physics that people understood at that time and what people were doing in chemistry. Then the nucleus was seen in 1911 from the Rutherford scattering experiments that led to the Bohr model, which suggested that there was some way to use electrons orbiting in some sense that atom that you could use to explain observations, such as, say, spectra, but also be the basis for chemical bonds. The only problem was the error model was full of errors. It only predicted basically one thing. Quantum mechanics pulled this all together in 1925 and also explained why the collisions between atoms and molecules were elastic. In quantum mechanics, you can explain that there are no internal degrees of freedom of that system that can be excited at the low energies encountered in thermodynamics. To see why this is so different from the things that are well described and very consistently explained in every physics textbook, let's compare that history to mechanics and electromagnetism. Newton's laws go back to 1687. Daniel Bernoulli, the same guy who came up with the idea for the kinetic theory of gases, developed a theoretical understanding of how a beam would deflect under a load in 1750 by using Newtonian mechanics and calculus. Engineering went from there. All sorts of things, like the things that we do in our mechanics class, were used to design things like the truss bridge shown in this picture, which was designed and built in 1903. It's still standing. I took that picture myself. 1903, a decade before atoms were discovered. Maxwell assembled all of the equations of electromagnetism into a work that was published in the 1860s, the first paper in 1861, and then a prediction of electromagnetic waves in 1865. Those waves were observed in 1888 by Hertz. Again, decades before the electron was discovered. We were using electricity to produce electromagnetic waves and radio long before we knew that there were electrons or atoms. Marconi sent a radio telegraph message across the Atlantic in 1902. That became a business before atoms were discovered. So that's the reason why I think statistical mechanics is necessary, and also why I think it's left out of our books. It's too new. It's only 100 years old. It's too new to be a standard topic within physics, and So we fall back on that stamp collecting approach in the textbooks that you see, like the one in our course.